All right, now I'm recording. Okay, so like I was saying, these alkali metals are stored in oil because they are so reactive, they'll react with the moisture in the air. They will not react, however, with oil. So they're stored in oil, and I'm going to take each one of them out and I'm going to put them into water. So I just have 3 beakers of water and each of the 3 alkali metals that I'm going to be working with. I also have tongs here because I'm not going to be touching the metals with my hands. They would react with the moisture in my hand as well, which would hurt. I have a glass stir rod here to stir in the universal indicator. This here is universal indicator. It indicates the pH of a solution. So that's going to be one of the color changes that we see in the reaction. Okay, so that's my setup, and I'm actually going to show you guys the reaction from above, which I think will be cool. Like so. And hopefully my phone doesn't fall in the beaker of water, because that would just stink. Okay, now before I do the demo, I want to talk a little bit about what is going to happen here. So let's now take a look here at my notes, and I would like you guys to write down a couple of things. So this alkali metals in water demonstration looks at the reactivity of metals. So one of the key things we're going to be looking at is degree of reactivity. And basically by reactivity, I mean like how fast is that reaction happening? How exciting is that reaction? Okay, so I want you to be on the lookout for signs of chemical change. Change, delta means change. And I want you to be on the lookout for the speed or exciting factor. Like on a scale of 1 to 10, how cool was the reaction? Okay, so the first thing that you guys need to know in order to understand what's happening here today is that metals react by losing their valence electrons. Losing their valence electrons. And remember our definition of valence electrons. Those are the electrons. Oops, sorry. It says my internet is unstable and my phone thing just popped back up. That's not what I want. Go away. Okay. These are the electrons in the outermost energy level. So those are the electrons that can get messed with. Now, in order for that metal to react, if it reacts really easily, so if it's easier for the metal to lose the valence electrons, the more reactive it's going to be. Okay, so like if those electrons come popping off very easily, you're going to see a really exciting reaction. If those electrons are harder to come off, the reaction's not going to be as exciting because the reaction is all about the loss of those electrons. So if they're easy to pluck off the atom, exciting reaction. If they're harder to pluck off, less exciting reaction. And I also want you guys to remember that we are going to be looking at the alkali metals. And remember, those are the metals here on my periodic table in group 1. Notice I did not circle hydrogen, okay? These right here are my alkali metals. They all have 1 valence electron. So we are going to look at lithium. Lithium has 1 valence electron. This is like my Lewis dot diagrams from yesterday. We're going to look at sodium. Sodium also has 1 valence electron. There it is. And we're also going to look at potassium. Potassium has 1 valence electron. And in this reaction, those valence electrons are going to get plucked off. Okay, hopefully you guys are still with me. I'm going to write one example of this reaction for you. So I could write this reaction for lithium or for sodium or for potassium, and you would just replace one metal with the other. I'm going to write the reaction for the lithium. What's going to happen is I'm going to take a solid piece of lithium, so lithium solid, and I'm going to put it into water. Now for our purposes, I'm gonna write water as HOH instead of H2O, because it'll just help you see what's happening a little bit more easily. This reaction, and you don't need to know these types of reactions, we're gonna learn them later. This reaction is called a single replacement reaction, because what's gonna happen is this lithium atom is gonna go into the water and it's gonna kick out this hydrogen. So that hydrogen is no longer gonna be part of the water. It's gonna come bubbling out as hydrogen gas, which is H2. So we should see bubbles of gas forming. Hydrogen gas also tickles the throat a little bit. It's not a toxic gas, but it is irritating to breathe in. So if you guys hear me coughing, I don't have coronavirus, at least not yet. I'm just breathing in too much hydrogen gas. But I've been doing a good job social distancing. I hope you have too. All right, so my lithium is kicking out the hydrogen, and now the lithium is going to be bonded to the hydroxide. And this is actually a solution, so I'm going to label it as aqueous. Lithium hydroxide, anything with a hydroxide in it like that, is a base, like the opposite of an acid. This is going to be basic. Okay, so that's an overview of what's going on. Now, the same exact reaction could happen with sodium and with potassium. Any questions so far before I actually pop this demo up in here? Okay, so now I need to get my phone screen working again. Oh, you know what? Maybe before I even do the phone screen again, I'll describe this. Let's see. Okay, so you guys already saw all 3 beakers of water. When I go to the share of my phone screen, I'm gonna drop in some universal indicator, which will indicate the pH of these 3 beakers. If these 3 beakers all just have water in them right now, my pH indicator should turn to green. It should appear to be neutral. So like, I'm gonna see like a nice shade of green in each of my beakers, indicating that right now they are neutral. So now I'm gonna see if I can get back my screen mirroring here. Oh, I saw a question pop up. Here we go. Does this work with all of the alkali metals except for hydrogen? Very good question, Julian. It works with all of the alkali metals. Hydrogen is not a metal, like you said, so it won't work with hydrogen, but it will work with the ones below it. I cannot get access to those metals, so I'm going to refer you guys to a video of what's going on with those metals, because I can't even get them because they are so dangerous. Okay, so now you guys should be seeing my phone. Hopefully we're seeing my phone up there. All right, and we're gonna go to my video. Okay. Eleanor, how are we doing?
You're doing good.
Okay, so what do you see?
The lithium beaker.
Awesome. Okay, so you see the lithium beaker, you guys, right? So what I'm gonna do now is, if we're looking at my beakers on my whiteboard as well, I'm gonna add that universal indicator, that pH indicator that I was talking about. And if that pH indicator turns green, we're gonna know that the water right now, before I've even added the metal, is neutral. And it's hard for me to tell whether or not I want more light in here, you guys. Hopefully you can tell that that is turning green. I'm gonna try with another light. Is that better or worse? Eleanor, what do we think?
It's about the same. It looks a little more yellow now.
Oh, okay. I'm gonna turn the lights off so that we don't have that glare.
Okay.
Okay, so you guys will take my word for it, it's green. Maybe you can tell from here better that it's green. Okay. So I'm gonna go ahead and add I'm going to add indicator to all three of them right now. You guys will be able to see that. So again, this indicator is just indicating that the water is currently neutral. Okay. Green, green, green. Okay. So now I'm going to go ahead and add my lithium to my beaker. If you guys want to see what these little pieces of lithium look like, I've just cut up some chunks of the lithium. They're kind of black in color because they've sort of oxidized with the air that is in this container. And I'm just going to grab one small chunk and plop it in there. It'll take a little minute for that oil to dissipate, right? So the oil and the water don't mix. So maybe if I give it a little stir. You guys should see the bubbling. You might even be able to hear it. Oh, I shouldn't stand right above it. Excuse me. And depending on how good your camera quality is or your computer screen is, you might even see that color change from green to purple. Good God. Look at what I'm doing for you guys. Choking. Okay. Voila. See this color change? What does this change to purple mean? When we saw the indicator turn purple, if you see my screen over here, purple means basic. So the fact that the color changed to purple means that we were producing a base, just like we predicted in that reaction up at the top. Okay. Now, before we move on to do a chunk of sodium, let's go back to our notes here for a second and describe what happened. So the lithium went in to the beaker and we saw those bubbles of hydrogen gas get produced. There's our product, the H2. And we saw the color change of the indicator to purple, indicating the presence of lithium hydroxide. Now remember, this happened because lithium was losing its one valence electron. Okay, so this one valence electron on lithium was getting plucked off. Where was it going? It was in fact going to the hydrogen. We're not going to talk about all of those details. That's for, later on in the year. But just know, lithium's electron got plucked off. On a scale of like 1 to 10, 10 being like that reaction was freaking awesome, to 1 being that was super boring, I don't know, what will we give it? Like a 3? It was like kind of exciting. We saw a gas get produced. We saw a color change. Let's rank it like a 3. And by rank, I mean like speed. How fast was that reaction? How exciting was that reaction? We'll say it was like a 3. Okay. Now we're going to do sodium. Moving over. You guys still with me? Eleanor?
Yes.
Excellent. Okay. All right, here goes my sodium. The sodium, you guys can see, is all the little chunks of sodium in there. Now, sometimes, if you guys know anything about hydrogen gas is explosive. So if there is enough heat present in that reaction, if that reaction is happening fast enough and we're releasing enough heat, sometimes you can get a little spark with the sodium. Sometimes it happens, sometimes it doesn't. So we'll just have to be looking closely here to see if we're going to get a spark. Can't guarantee it. you guys probably can't hear it this time because I didn't lean in so that you could have the mic over it because I was choking so bad last time. Okay. I didn't see any sparks, and you guys probably couldn't hear it, but that one was a lot faster. Like the production of the gas was like, psst. Should I do another piece? Let's do one more. Let's see if we can get a spark. Come on. Nope, it doesn't feel like sparking today. Not today. All right. Again, the purple color, the production of a base. Let's go back to our notes. Okay. So the sodium went into the water. A little chunk of sodium goes in. Oh, it just started reacting again. Hydrogen gas bubbling up at a much faster rate. Again, you guys might not have heard it, but it was like bouncing all over the container, right? Which means that hydrogen gas was being produced a lot faster. It's the production of the bubbles of gas right around the piece of metal that send that piece of metal flying all over the beaker. The lithium kind of stayed in the same place and just produced gas. And the lithium was kind of like ding, 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 all over the place as that hydrogen was produced faster. And again, we saw that color change to purple. This time, the production was sodium hydroxide. So if I had to rank that on exciting, I don't know, maybe I would make that a rank of 5. Like, it happened, it was definitely faster. Okay, so like this one was slow, this one was faster. Okay. Let's do potassium. See, here are my chunks of potassium. Into the beaker. Ooh, I hope my phone's okay. You guys see the sparks that time? Hopefully. It's much more fun in class when I hear you guys go, oh, do a bigger piece. I don't have any bigger pieces. These are the only ones I was comfortable bringing home from school. Sure enough, if I brought home a big chunk, one of my children would find it and blow up the house. All right, here's another piece, potassium. Really fast reaction and releasing enough heat for that hydrogen gas to ignite. Where do the release reactions from the sample go? Excellent question, Anthony, and I will explain that at the end. So I wasn't going to get into it because it's a little bit complicated, but you guys ask really good questions, so I will explain that, but just hang tight for a second. We'll do that at the end. Okay, so hopefully you guys would agree with me here that that last one was the most exciting, right? So on this potassium example, potassium goes in, immediately lots of hydrogen gas produced, and we got flames. The hydrogen gas ignited into flames. And of course, we got that characteristic purple color again because we produced potassium hydroxide. And so if I was ranking that, this was my fastest and most exciting because of the flame. I would rank that, I mean, listen, if you had a big chunk, it would be super exciting. I don't know, let's call it a 7. Okay? This is my fastest. So what I want you guys to recognize about what's happening here is if we look at the periodic table, as we went down this group, when we went from, so this is my lithium beaker, to my sodium beaker, to my potassium beaker. As I went this way, the reaction got more exciting. the reaction was faster. And by being faster, what that must mean is that the electrons were removed more easily as we go down the group. Like potassium's 1 valence electron was easier to pluck off than sodium's or lithium's. And that's that question Anthony's wondering about. It's like, where'd those electrons go? Okay. So the questions that we're going to answer tomorrow is why? Why are potassium's electrons removed more easily? The ability to remove electrons more easily is based on something, and you don't need to write out all these definitions yet, but we're going to learn about them tomorrow, is based on something called ionization energy. This is the energy needed to turn something into an ion. This is the energy needed to remove an electron. Energy needed to remove that valence electron. So if this one was easy to remove, it must have meant that it had a low ionization energy. And then your next question must be, well, like, why? Why does this have a low ionization energy? Why is this electron easy to remove? It's because potassium has a very big atomic radius. Those electrons in potassium are really far away from the nucleus. They're in that 4s orbital. And so if they're really far away from the nucleus, they're really easy to remove. So we're going to learn all about tomorrow. We'll take much more detailed notes tomorrow that talk about definition of ionization energy, definition of radius, and those two things together are going to be able to explain why potassium was so reactive and lithium was not. So if we were to look down here at the periodic table, what we're going to find tomorrow is that when we go down a group, any group, it doesn't have to be the alkali metals. When we go down a group on the periodic table, they get more reactive. Well, the metals do. Okay, so when we went down this group, we saw that it was more reactive. And Julian was asking the question, why did you stop at potassium? Why didn't you also show me rubidium and cesium and francium? It's because I don't have those metals. And so if you want to see a video of those 3 metals reacting with water, I want you guys to go to Google Classroom, where we've been posting the week 2 materials. And we linked to a video called Brainiac, Alkali Metals, or you could just Google it. You can either Google it on YouTube or go to that link on Google Classroom if you want to see those 3 metals react with water. So the reason why these things are getting more reactive is because they have lower ionization energies and they have bigger radii. But again, we're going to talk all of that in detail tomorrow. So that is it for the demo, you guys. I do want to stay and answer questions that you guys have. And tomorrow we'll finish up the notes on this topic. But I did want to go back up here and answer the question that, that Anthony had about, well, where are those electrons actually going? This is a little bit complicated, so nobody actually needs to know this, but it is kind of interesting. If I'm looking at this reaction right now, I can assign these numbers called oxidation numbers, which is just basically like a measure of who has electrons and who doesn't, or who has like extra electrons or who's lost electrons. So if I were to assign these oxidation numbers here, I would assign lithium because it's a metal and it's a solid and it like hasn't gained or lost electrons yet. I'm going to give it a number of 0. And hydrogen, because that's the elemental state of hydrogen and it hasn't gained or lost electrons yet, I'm going to give it a number of 0. Now, it turns out that the hydrogen in water, this front hydrogen in water, it has a charge of a +1. And this lithium here in this reaction has a charge of or compound I should say, has a charge of a +1. So what you might notice with these numbers, even though you sort of don't know where they came from, because we just haven't gotten this far in what we've learned yet, what you guys might notice is that lithium is going from a 0 to a +1, which means it's losing an electron. Like that's how things get positive charge. Remember my dumb joke? I'm hit, I've lost an electron. Like, are you sure? Like, I'm positive. If you lose an electron, you get positive charge. So that's what I was saying. Remember I was saying that like in these reactions, lithium is going to lose its valence electron. And then Anthony's question was, okay, fine, but where is it going? Look at what's happening to hydrogen. Hydrogen in the water has a 1+ charge, but then hydrogen in the product as the gas has no charge. How do we go from a positive charge to no charge? It must have gained an electron. So where did that electron go? It went to the hydrogen. Okay, so like lithium had an electron to lose, and that water molecule had an electron that it wanted to gain. And so that electron transferred from the lithium to the hydrogen in the water. Once that hydrogen got that electron, it bonded to another hydrogen and bubbled out as hydrogen gas. So that's like way more chemistry. That's like the stuff we're talking about in AP chemistry right now. These are called redox reactions. So good job being curious about that, but nobody needs to, yeah, Raj is asking, how does one hydrogen turn into H2? Raj, this reaction is not balanced. So one of the things that we're gonna learn this year is putting these coefficients out in front of our chemical equations. So you're right, one hydrogen can't turn into 2. We would need to balance this equation with something called, well, not something called, with coefficients. You guys know what coefficients are. So if you see on the left-hand side of my reaction right now, I have 1 lithium, and on the right-hand side, I have 1 lithium. So that's balanced. And on the left-hand side, I have 1 hydrogen in the front here, but I have 2 hydrogens here. So I would need a 2 out in front here. So Raj, you're right. I would need 2 water molecules in order for this to happen. And then of course, if I have a 2 out in front here, that means I have 2 of these hydroxides, right? So I would need a 2 out in front here. That means I've got 2 lithiums. So now I need a 2 out in front there. Again, that is getting way ahead of ourselves, but excellent, excellent questions. So we're gonna learn about all this stuff, you guys. We're gonna learn about how to write chemical reactions, how to balance chemical reactions. Stick around next year for AP Chem to learn about these redox reactions and the gain and loss of electrons, which is a lot. All I want you guys to leave today with is like, alkali metals, they lose those 1 valence electron. And I want you to remember how to draw Lewis dot structures. So like lithium, there's its 1 valence electron. Sodium, there's its 1 valence electron. Potassium, there's its 1 valence electron. And I want you to recognize that as we go down that group on the periodic table, those electrons are easier to pluck off. And tomorrow we'll explain why. Okay, so I'm gonna stop recording.